Okay, so thank you very much for the invitation. I'm really happy to be here. So I'm going to present a joint work with Claude, Sabbah, and Jeng-Daw. So the paper will be on the archive tomorrow, but in case you really cannot wait, which I, of course, would understand, it's also on my website. And I should say that we were very much inspired by, well, several people, but I should name, well, my joint work with Peter. So in particular, you will see we are going to construct some classical motifs, but the way they will be constructed is first as exponential motifs, and then showing that they are indeed classical. So we will use the kind of ideas that were explained at the very end. And also, I should name David Broadhurst and David Roberts. And actually, the whole project started so we were trying to understand some amazing numerical computations they were doing, and that was really the motivation. Okay, so first I will state the main theorem, and this is going to be very concrete number theory for maybe 5 or 10 minutes. But don't worry, there will be L-adic shifts, there will be motifs, and you just need to wait a little bit. Okay. So the situation is the following. I work over a finite field Fp, and then I will fix an algebraic closure. And when I talk about Fq, I mean the subfield with Q elements in this closure. And I choose a non-trivial additive character of this field. So for the moment with complex coefficients. And as you will see, you will not lose anything in assuming that this character is exponential 2 pi I over p, and then your element of the finite field. And yeah, so then you can define Klosterman sums. So there's one for each element in Fq star, and they are defined as follows. So you will sum the values of the character on the traces, so from Fq to Fp of x plus a over x. Okay, and then x is a point in Fq star. Okay, so this is a priori a complex number. You can actually show that it's real. And as an application of the Riemann hypothesis for curves over finite fields, Bessel showed that you can always write this number as a sum of two algebraic integers. So there exist algebraic integers alpha a and beta a, and such that KL2 is equal to actually minus the sum of these numbers, and then their product is equal to Q, and then they have absolute value a square root of Q. Okay, so this will of course be eigenvalues of Frobenius in 5 minutes. And once you have these numbers, you can define symmetric powers of these sums. So if k is an integer, at least one, then you define KL2 sim k. It still depends on the parameter a. Well, as the sum of all monomials of degree k in these alphas and betas. Okay, and the thing we really want to study is so not these ones, but what people usually call the moments. I'm going to denote M2KQ. And those are defined by taking these symmetric powers and then summing overall values of A. Okay, and then you can easily see that, well, first of all, these are integers. Because you will prove that the Galois group permutes the symmetric powers corresponding to different A's. So when you sum over all of them, it becomes invariant. And then more or less the same proof also shows that they are independent of the choice of the character. They are independent of choice of psi. Okay, so of course the Klosterman sum depends on the choice of the character and also the symmetric powers, but then when you sum over all A, it doesn't. And this was somehow the first indication that this a priori exponential thing could indeed come from something classical. Okay, and then what do we do with these numbers? We are going to put them in a generating series. So I look at the exponential of the sum of the moments as Q runs over all powers of P. And then as usually the best normalization is to put Tn divided by n. And then this a priori formal power series, it's indeed a polynomial. So this is a polynomial with integer coefficients. And you can show, I will indicate a bit later how, that it always contains some so-called trivial factors. For example, this polynomial is always divisible by 1 minus t. So it's better to remove these trivial factors, and then I'm going to call mk the remaining part. So this will be the quantity of interest for us. And you can compute the degree. So the degree of this polynomial mk. So this is equal to yeah, so it's, let me give you the degree in the case k is odd. So in this case, it's equal to k minus 1 over 2 if p is equal to 2. And it's k minus 1 over 2 minus, so integral power of k over 2p plus 1/2 if p is bigger than 2. And it's a similar formula, it's a bit more complicated in the case where k is even. And here you already see that, okay, so there are some prime numbers for which the degree is smaller than expected, but as soon as p is large compared to k, and in this case it has the very precise meaning p is larger than k, then the common value of the degree is k minus 1 over 2. Okay, so later on there will be a situation in characteristic 0, and then this degree will be the dimension of the RAM cohomology group, and it will take the common value k minus 1 over 2. Okay, so I want to denote by S the set of primes for which the degree is smaller than this common value. So these are the odd primes smaller than or equal to k. And then I I defined, so everything so far was local, so I was working with a given finite field Fp. And now I want to globalize, and for this I consider the following Euler product, where I take the product over the primes which are not in this set S of bad primes. And then the local factor is the inverse of this polynomial computed at t equals p minus s. And one of the advantages of removing these trivial factors is that the reciprocal roots of this polynomial, they all have the same absolute value. So once you do this, the roots have absolute value p to the minus k plus 1 over 2. And in this way, you see that this product converges if the real part of S is bigger. So as usual, is 1 plus the weight. So it's the weight over 2. So in this case, it's 1 plus k plus 1 over 2. Okay. So I'm only, for the purpose of this talk, I'm only discussing the case where k is odd, because everything is simpler, and there are similar results in the case where k is even. Okay, so I think I have everything now. So here's the theorem that Claude, Jeng-Daw, and I proved. So it has two parts. The first part is that this function has a meromorphic continuation to the complex plane. And the second part is that it satisfies so when you meromorphically extend it, it satisfies a functional equation. And then this functional equation is given as follows. So, well, as usual, if you want a neat formulation, this is not the right object, so you need to complete by putting local factors at bad primes. You also need to put gamma factors at infinity, and then there's also some conductor appearing in the functional equation. So in these situations, we can make everything very explicit. So we define the completed L function as follows. So here is the conductor. So the conductor is the product of odd primes up to k, except that for each of them, if they are divisible by a square, you remove the square. Okay, so this is supposed to mean, so ns is supposed to mean a square-free part. Okay, so if you find the number 9, then you put 1. If you find the number 27, then you put 3. So of course, that doesn't mean that the thing is square-free, because you will find 3 when you do 15 again. Okay, so this is the conductor, and then we have a product of gamma values. Sorry. And they are these ones, and then they go from j equals 1 to m. So I'm sorry I didn't say what m is. So k is odd, so we write k as 2m plus 1. Okay, and then I put my function defined as an Euler product, and I still need to put bad factors so local factors at p in S. Okay.
Here you have 3 different S, right?
I think there are only two of them. One is supposed to be a capital S. So this one is a big S. And oh yeah, I see. Yeah, sorry. Okay.
Okay.
Yeah, sorry. Yeah, so this is the way you complete the function. So I'm not giving the shape of the local factors because it's a bit complicated, but it's very explicit. You can have a look at the paper if you want. Okay, so the statement is once you complete the function this way, it satisfies the functional equation. The value at s is equal to the value at k plus 2 minus s. Okay, so in the terminology of Peter, there was a bit of pain along the way, but then the result is very nice. Okay, so that's the theorem I want to discuss. And so you can imagine the only way to prove such a thing is to construct a Galois representation that has this kind of numbers, the moments as traces of Frobenius, and then show that this Galois representation is automorphic or potentially automorphic. So this is what we do, and for this, luckily, we had a very powerful result of Patrikis and Taylor. So I will explain how we construct the Galois representations, what this result is, and then somehow the crucial point to prove that the result applies is to show that the Hodge numbers of the motif we are going to construct are 0 or 1. And this will be explained in the next talk by Claude, because this uses some Hodge theory characteristic of exponential motifs. Okay, so yeah, so let's go. First, I go back to the situation over finite fields, and now I give you the cohomological interpretation of everything I was doing here. So Klosterman Sums, symmetric powers, the moments, so everything are traces of Frobenius of L-adic sheaves. So now I'm going to choose L different from P, and then the character will take values in QL bar now. Okay, for this, of course, at least I need to embed the pth roots of unity in QL into C. So there's some choice involved. And then we will consider the following diagram. So here I have the two-dimensional torus with coordinates x and z. And I consider the function to P1 to A1 given by x plus z over x. Okay, so in such a way this becomes a variety with potential in the terminology of the previous talk. And here I want to look at the projection to the z coordinate. So pi is the projection. Xz goes to z. Okay, and then associated with the character psi, we have an L-adic sheaf on A1, which is the Artin-Rae sheaf. So it has the property that if you take a point, and so an FQ point on the affine line, then the Frobenius will act on the fibers of this sheaf as multiplication by exactly these things, so the value of the character at the trace of this point. Okay, so it is the beginning of the interpretation of these sums in cohomological terms. And then if you, instead of summing x, you want to sum the value of the function, well, the thing to do is to take the pullback. So the next step the next step here is to take the pullback of the Artin sheaf by the function. So in such a way we get a L-adic local system on GM square. But then we still want to sum over all values of x. So this means that I will consider the cohomology with direct support along the fibers of the map, and okay. So you can first consider the whole cohomology, and the linear proves that it is concentrated in degree 1. So it makes more sense to do R1. So this will be a sheaf, and this is by definition the Klosterman sheaf. Okay, so this is the Klosterman sheaf. Okay, and then the linear. So he proves that well, it is a rank 2 Lie sheaf on GM. Okay, so L-adic local system of rank 2 on GM, and it is pure of weight 1. So this happens. This comes from the fact that here I consider a compactly supported cohomology because this is the one which has a natural interpretation in terms of sums. But you could have considered usual direct image, and then there is a map from one to the other, when you forget the supports. And then what the linear proves is that this map is an isomorphism. Okay, so then, for example, by veil 2, this thing has weights at least 1, and this thing has weights smaller than or equal to 1. So it's pure of weight 1. Okay, and then in this interpretation, so what are the eigenvalues? What are these algebraic integers? So these are the eigenvalues of Frobenius acting on the fiber. So alpha A, beta A. So these are the eigenvalues of Frobenius acting on a geometric fiber of the sheaf above A. So then the property being pure of weight 1 is telling you these estimates for the absolute value, and yeah, so the. Yes, I think we know. Yeah, maybe it was proved by Katz. Yeah, I'm not sure. It is, but I don't think it's in the linear. Yeah, and yeah, okay. So there's a minus here. The minus here comes from degree 1 and the cohomological conventions. But otherwise, so the trace of Frobenius at A is exactly this sum. Okay. Okay, so this was for the Klosterman sums. So then we did the symmetric power. So in these terms, this means so you have a L-adic local system. So you can think in terms of representations of the étale fundamental group, and you are just taking the symmetric powers. Okay, so the traces at a point A will be these sums here, and then doing the moments means passing to cohomology. So the thing we will be interested in is well, in first approximation, the étale cohomology with compact support of this sheaf on GM. And yeah, so I said KL2 is pure of void 1. So when you take the symmetric power, is pure of void K. But when you take the cohomology, it gets mixed. So these trivial factors I was explaining there, they come from, sorry, so you will have a map from this H1 with compact support to usual H1. And then this sits into a long exact sequence. What comes here are the invariants of inertia at 0 and infinity, then the co-invariants, and then these factors come from there. So if you want to just look at the pure part, the good thing to do is to take the image of this map. Okay, so this I'm going to denote H1 et al. Mid of GM sim K. Okay, so the terminology is supposed to refer to middle extension. Because you can also compute this as the cohomology on P1 of the middle extension of the sheaf. Okay, and then this is pure of weight K plus 1. And the polynomial we had there, MK, this is exactly the characteristic polynomial of Frobenius acting here. Okay. So that's the situation over finite field. So now I want to imitate this construction in characteristic 0. Okay, so I will just consider the same diagram as before, except that now we work over, let's say, over Q. And now I need the analog of the Artin-Ryer sheaf, and this is the differential equation of the exponential, which has the advantage that it doesn't depend on anything. Okay, so here I will consider exponential of x, which is the trivial rank 1 vector bundle A1 with the connection given by d plus, well, maybe d minus dx. Okay, so when I pull it back, I get. So if I pull this back, well, I get what is reasonable to call exponential of f. So this is now the trivial vector bundle on GM square with the function with the connection d minus df. And if you look at the RAM cohomology of this complex, well, if you look at the RAM complex and you compute the cohomology, then you find the RAM side of the story Peter was telling. So he only told you about the singular side, but this will be the RAM side. Okay, so we are here, and now we do the same thing. So we take cohomology along the fibers. So KL2 is. Now we take a direct image in the sense of D module, so it's written like this. And this will be our Klosterman object on GM. So what is this object? Well, in the same way as this one was an elliptic sheaf, this is a vector bundle with connection, so it also has rank 2. So it's a rank 2 vector bundle with connection on GM.
So what is the justification for on the elliptic side we have shrink until we have 5 bars?
You can also do the other one.
Okay.
Yeah, it's just since I explained that the two were isomorphic.
I understand.
No? Yeah, in this case, this is how you prove that it is pure of weight. Yeah. I think so, yeah. It's just, here I'm going to explain this now, so I would like to think of this as a family of exponential motifs, and I want to take usual cohomology, not compact support cohomology. So here I was a bit forced because what has an interpretation in terms of sum is compact support. But, yeah, thank you. Okay, so it's the rank 2 vector bundle with connection on GM. Actually, it corresponds to the Bessel differential equation. Okay, and if you want to be precise, it's the modified Bessel differential equation. So which is the order 2 equation like this. Okay, so modify means that you have a minus instead of a plus. And the solutions, the two linearly independent solutions of these equations are these functions Peter was showing, so that he called J0 and H0. And we would like to think as GL2 as a family of exponential motifs. H1 GM x plus z over x. Okay, as the parameter set varies. And actually, so the periods of these motifs will be the values at z of the Bessel functions, and they indeed satisfy this differential equation. Okay, so this will be the object, and yeah. So what am I going to do now? I will look at the RAM cohomology of symmetric powers of KL2, and in the different flavors, so compact support, usual, middle extension, and then I will. The goal is to show that this the rank cohomology, which is a priori the rank cohomology of so this differential equation has an irregular singularity at infinity. So it's a priori an object which doesn't come from geometry in the usual sense, but when you take the cohomology, it's actually the RAM realization of a classical motif. And this will give us mixed Hodge structures and Galois representations. Okay, so let's go. So the goal is to look at H1 the RAM mid GM sim K KL2. So again, define as the image of compactly supported the rank cohomology and usual the rank cohomology. And for this, I will start with usual H1 the RAM. And then I'm going to transform this cohomology using every time rather elementary tricks. And at the end, it will be clear that it's, well, in the middle, it will be clear that it is the rank cohomology of a variety with a function, which is still not clear. And then I will show that it is actually the rank cohomology of a variety without a function. Okay, so how do you do this? So the first step is to look at symmetric powers inside tensor powers. So you can, instead of sim KL2, you can consider KL2 tensor K, and then you consider the action of the symmetric group. And then, because of the cohomological degree, this action will go out with as the eigenspace for the sign of the permutations. Okay. So the second step is to use this description here as KL2, so it's this direct image, and then you combine this with the QNet formula, and so there's a little bit of work here, but you show that this is the same thing as cohomology in degree k plus 1 of GM k plus 1, and now together with a function. So let me write the function fk. So I still have the invariance by the sign. So we're now where fk is so here I have coordinates x1, xk, and then z, and then fk is a function that you will recognize. So it's the sum of the coordinates, and then it's plus z multiplying the sum of the inverses of the coordinates. Okay. Well, I didn't write it down, but what I mean by the RAM cohomology of a variety with a function is you take the RAM complex of exponential of f, which is simply Ox goes to omega 1 and so on, but by d minus df, and then you look at the cohomology of this complex. Okay, so it's one the RAM x comma f. This is the cohomology of this complex. Okay, so here we are in business. So this is the RAM realization of an exponential motive. And now the very innocent but crucial observation is that if you replace z by z squared, then this function is much easier to study. So, and you will see why. So we are going to pass, this means consider the degree 2 étale cover of GM. And that sends z to z squared. So it's going to be called t now. And then, okay, so I continue here. So this will be equal to the pullback of the function. Yeah, so I take the pullback of the function, and then I take the invariance under the action of mu2. Okay, so this is hk plus 1, the RAM, so gm k plus 1, and then the function. But when you do the reason why we do this is when you change z to z squared, you can put it out as a factor. Okay, so then this function becomes t times another function, maybe fk tilde, and then there is the sign, and then there is the invariance under the action of mu2. And then this function here is now just sum of the coordinates plus sum of the inverses of the coordinates. Okay? And now the proposition I want to use is that if I have an exponential motive of the form, so I take a variety x, so it comes with a function f. I take the product with the affine line with coordinate t, and then as a function I put t times f. Okay, you see it's not quite our situation, but we are not very far. So then the statement is that this a priori exponential motive is always classical. So it's always a classical motive. So this is something you can prove, for example, using, there are several proofs. You can prove this using the criterion that was given by Peter. So you show that the perverse realization of this is trivial. So then it comes from a classical motive. Or, for example, in the case where the zeros, where the zero locus of the function is smooth, and this is true in general, but let me say x is smooth, and then the zero locus of the function is also smooth. Then this motif here is actually nothing mysterious, so it's hn minus 2 of the zero locus, and then you twist by minus 1. Okay? And this identification between these two motifs should remind you of the following. So here if you look at exponential periods of these things, so you will find integrals of the kind exponentials minus tf, and then a differential form on x, and then dt. And if you integrate over appropriate cycles, there's a way to write such an integral as 2 pi I, and then the integral over well, something on Z of the residue of omega over f. Okay? So precisely what you need to do is you take a cycle on Z, and then you can inflate this cycle to the complement through the tubular map, and then you integrate from 0 to infinity, and then on this tubular map. Okay? So the fact that these two motifs are isomorphic is some kind of cohomological translation of this. Okay, so we want to apply this, and as I said, here we don't have A1, we have a GM. So you can pass from one to the other, and then you will find some exact sequences. This is the place where you introduce mixedness. So the thing starts to, because of this, the thing is not pure anymore. But at the end, if you work this a little bit, at the end what you find is that, so at the end you find that this is the rank homology from like the middle extension, the rank homology. It's actually isomorphic to the following thing. So X is a toric hypersurface, and is the one defined by the zeros of this Laurent polynomial. So this one is defined by this is equal to 0. And then what you do is you take cohomology in degree, so this has dimension k minus 1, you take middle cohomology. Okay, you don't forget these operations here. So they translate to, sorry, so this translates to an action of the symmetric group permuting the coordinates, and an action of plus or minus 1 sending x to minus x. So you take the sign character and then the invariance. You take the weight part of degree k minus 1, and you twist. Okay, and then you find that these two things are isomorphic. So this is the proof that this is the ramp realization of a classical motif.
Do you think that the compact supported and the other ones are also just provided?
Yeah, this is a bit tricky. Very good question. So usual motifs inside exponential motifs are not closed under extension. So this was true for perf 0, but it's not true for exponential motifs. And this creates some problems. So I think we don't know how to show that each of them is classical, but it works for the middle extension, and it also works in the context of Hodge theory. This will be explained by Claude. So there's exponential mixed Hodge structures inside, and in that case it works for the three of them. But there's some extra missing thing to do. Yeah. Okay. So any other questions?
You were dealing with some Norn categories.
For the
no motives are not closed under extension.
No, I just wanted to know what closed under extension meant. Because I thought we were like, I forgot what category it was calling it, DM or MMK.
No, so these are two categories constructed in the style of Nori.
Yeah.
So one is the usual one, and the other one is the exponential.
Yeah.
The usual one is a full subcategory of the other one, but the image is not closed under extension. It's a very interesting story when you find the Euler constant gamma is a period of such an extension and so on.
Which we know from a paper of yours.
Yes, that's true. We took the integral representation from your paper, yeah. Thank you. Okay, so what are the consequences of this? So two important consequences. So first one is that this the rank homology carries a mixed Hodge structure. I will put it out of the shadows. So H1, the RAM mid, has a mixed Hodge structure. So as yeah.
Excuse me, is that what you cover? Because don't we know something Jeng-Daw?
No, what we know is that so there's, I think Claude will explain this. So there's a category called exponential mixed Hodge structure. So this is defined in the same way as Peter defined perf0 using perversives. You replace perversives with mixed Hodge modules on the affine line, and you do the same. Okay, and then you have the RAM part.
Mixed Hodge structure means the exponential sense.
No. Here, this side of the equality has an exponential mixed Hodge structure. Yes. The other one has a usual mixed Hodge structure, yes. and well, they are compatible. So that's the statement here. Yeah. Okay, and then the theorem Claude will explain is that the Hodge numbers are the following. So you have 2, k minus 1, 4, k minus 3, up to k minus 1, 2. So they are equal to 1, and all the rest are 0. Okay, and somehow this is the crucial part of the argument to be able to apply these results from automorphic. Okay, so that was one. So this you wait for Claude. And then yeah.
Do you need that to be able to use the number theory? Like say there's some number theory thing that makes it so.
No, this doesn't use any number theory.
No, but I mean, do you need it to use the number theory thing to get the automorphic?
This one?
Yeah.
Yes. You will see the statement, and this is the most important part. Yeah. Okay. Those second consequence is that well, we get Galois representations. So for each L and each K, there's a continuous L-adic representation here. Okay, and I said it a long time ago, but I didn't say it again. So this M here, so it's the dimension. So M is equal to K minus 1 over 2. Okay, so this was the common value of the degrees of the polynomials. Okay, and then these Galois representations have the property that they are unramified at primes not belonging to big S. Okay, so if P is a not prime which is larger than K, then it's not, okay, I'm again discussing the K case, so then the representation is unramified. So you can look at the image of Frobenius at P, and then the trace will be, well, up to sign and up to this minor correction coming from the trivial factors. So these are the moments. Okay, so this is minus M2Kp minus 1. Okay, and this is proved using the fact that, so I explained that these numbers were the traces of Frobenius on the middle extension cohomology of the L-adic sheaf. And if you go through this argument, this only uses cohomological exact sequences, QNet, and so on, and everything exists in the L-adic world. And the same argument shows that the traces here are the ones given by the other one. And this one comes with a Galois representation because it's geometric. Okay. And yes, yes, it's already, yeah. Yeah, it's over QL. Thank you. And here I should mention that these representations were, representations doing the same thing. They were constructed before by Siwei Yun. So he constructed such a representation. And he also proved that they appear as a sub-quotient of the cohomology of a smooth projective variety. So it's a cohomology which is cut off the affine Grassmannian. And so in particular, the up to semi-simplification, the two representations are of course the same. But this description somehow is easier to compute the Hodge numbers and things like this. So at least I couldn't do anything with the other description.
What is capital S?
Capital S is the odd primes smaller than or equal to K.
And what about L? It should be also
yeah, sorry. Of course. Yeah.
Can I ask?
Yes.
You probably show something with general Klosterman sheaves, where you take any reductive group in any representation.
No, we didn't go that far. So we do the thing in any KLN, so in any number of variables. But yeah, so this works for Klosterman sheaves of reductive groups. And somehow it is maybe the continuation of the story to try to do similar things in these cases. Okay, so yeah, so how much time do you have? Okay, 6 minutes. Okay, so yeah, so let me tell you the result of Patrikis and Taylor we use. So it says that if you are given a compatible system of L-adic representations, actually they call it a weak compatible system. And then it satisfies the following three conditions. So then the conclusion will be that over some extension, it becomes automorphic. And then the consequence for us will be that the L function has a meromorphic extension to the complex plane, and it satisfies a functional equation given by epsilon factors in the automorphic setting. So this will give part one of the theorem, and then there's still some work to prove that this functional equation is actually the one I wrote. Okay, so let me tell you the condition. The condition is so purity. Okay, so it means that at primes which are unramified, then the roots of the characteristic polynomials will be Bale numbers of a given weight. So in our case, this is okay. So this thing is pure of weight k plus 1. So for us, it's k plus 1. Then there is regularity, which in this context means that the Hodge state weights are distinct, so there are no multiplicities. And these multiplicities, when you have a representation of this shape, are exactly the Hodge numbers. Okay, so here Hodge state weights distinct, so this translates into Hodge numbers in the sense of Hodge theory, 0 or 1. Okay? And then this is the thing that is provided by the theorem. And then there's a third condition, which is that the representations are either orthogonal or symplectic. Okay, so 3, orthogonality, or symplectic. I don't know how to make a noun, but it's symplectic. So this means that for example, this means they factor through GOMQL, and then you also want to say something about the similitude character and so on. Okay, so if you have and this is true in our case because this motif here comes with a H1 the RAM so middle GM sim K. So this comes with a perfect pairing. Which is minus 1 to the k plus 1 symmetric. Okay. So this comes essentially the dual of a motif of a variety X F will be, well, I'm simplifying a little, that will be the compact support cohomology of X with the function minus F. But in this case, the two functions are isomorphic. So you get something like this. So this is what allows you to prove orthogonality. Yeah, and then what's the conclusion of the theorem? So the conclusion is that then the partial L function. Okay, I just write the one I was looking at. In general, it will be the one constructed out of the representations at the unramified primes, then extends meromorphically and has a functional equation.
What is the first condition?
Purity.
Purity.
Yeah. Yeah. Sorry. Okay, so once you know this, as I said, the remaining work is to show that the functional equation is exactly of the shape I gave. So let me just make a few comments. So this variety here, X, is smooth over Q, because the singularities have to be 1 or minus 1, and then you cannot put them up to 0. But it is singular if you reduce modulo p for odd primes smaller than k. So this explains, for example, this set S here. So, and then these were the primes dividing the conductor. So this is one thing. Then the Hodge numbers give more or less the shape of the gamma factor, except that you also need to look at the action of complex conjugation when you have classes of PP. And then there are two ways to do this. One way is to compute the determinant of a period of Bessel integrals and see if it's real or complex. And then the other way that was explained to us by Takeshi is okay, this is an orthogonal motive, so it means the determinant is a twist and then the character of a quadratic number field, and you need to decide if it is real or imaginary, but you can compute the determinant, and then you see that the determinant is not ramified at 2, and this fixes the sign. Okay, so in this way you compute the gamma factor. So the local factors are bad primes, the singularities are not too bad, so they are quadratic points, so you can use the Picard-Lefschetz formula, like rather detailed study gives the shape of the factors. And then for the only remaining thing, once you've done all this, you know that the functional equation is plus or minus, and you need to determine the sign. And for this, we used Takeshi again. And he has this beautiful theorem that orthogonal motive of even weight has, well, if it satisfies some compatibility condition, which is satisfied in our case, then the sign is always plus. Okay, so that's it. Thank you.